Greetings, AP Chemistry, and welcome to your very first Thanksgiving break podcast. What am I thankful for? I am thankful for chemistry. I am thankful for you and your hard work, and I am very thankful, guys, for intermolecular forces, which is the topic of our discussion here throughout Chapter 13. So, what we're going to start with today, our first podcast, is I'm going to introduce you guys to the three main kinds of intermolecular forces experienced by solids, liquids, and gases. Okay, in our next podcast, we're going to look at liquids and phase changes, and then finally solids and their properties. So we're going to try to keep this brief into three different sessions, and with each session, you're going to have an associated problem set to do. So here we go, guys. I hope you enjoy this as much as I do. All right. So, let's first, before we really jump into it, let's define the difference here between what I like to call intra and intermolecular forces. If we look at the root of the word, an intramolecular force would be something that works within the molecule. That would be like a chemical bond. Okay, so let's consider an example here, which would be water. Okay, if we look at the water molecule, here is a Lewis structure for the water molecule. We're going to look at water a lot, actually, in this chapter. And here we have two pairs of non-bonding electrons up there on that central oxygen atom right there. This molecule is held together here by covalent bonds. It has two covalent bonds, in fact, from the central oxygen to the hydrogen atoms there. Okay, that would be an intramolecular force, rather, that holds that molecule together. Okay, now if you look at a sample of water, though, if we go pour ourselves a glass of water out of our sink or whatever, that glass of water is going to contain a whole lot of water molecules, trillions and trillions and trillions and trillions, and those molecules are all attracted to each other. So if we look at these separate water molecules, these are attracted to each other through something called hydrogen bonding, which we'll talk about here in a moment. But this attraction between the water molecules, that is an intermolecular force of attraction. Inter meaning between. So these intermolecular forces, if you wanted to define these are the attraction or the forces of attraction, okay, that are at work between molecules, okay, of a given substance. Now, you might ask me, Mr. Harper, are intermolecular forces important, and why are we spending an entire chapter on them? Well, the reason why is because intermolecular forces and their relative magnitude are what determine the properties, okay, of a substance. They determine the melting point, the boiling point, viscosity, surface tension, how they work by capillary action, and all kinds of other stuff for a different substance. It is, in fact, intermolecular forces that keep you in a mostly liquid state. Star Trek phrased it most appropriately when this alien species described the humans on the Starship Enterprise as bags of mostly water. That is true. You are a bag of mostly water. And the reason why you do not boil when you walk outside into the sunlight and start absorbing all that thermal energy is due to the magnitude of the intermolecular forces acting between water molecules. Okay? And that is what determines the fact that water has a boiling point of 100 degrees Celsius. Okay, so this is what determines when things change state, when they boil, when they freeze, when they whatever, okay? It determines solubility, so when things dissolve, it determines how much you can dissolve and whether it will dissolve in a given solvent. It determines the three-dimensional structures of proteins and DNA. Proteins and DNA both have a characteristic shape, and that shape is important to their function. The thing that holds them into the shape that they have, so in the case of DNA, that would be a double helix, and proteins have various geometries depending on the amino acid sequence. The reason why they have the shapes they do is because they're held together in a particular conformation by intermolecular forces acting between the parts of the molecule. And this is the entire reason why, guys, there are three phases of matter. If there were no intermolecular forces, everything would be a gas. Now, why is that? What's the difference, in fact, between solids, liquids, and gases? We're going to talk more about this idea called the kinetic molecular theory, which describes the way that gases, solids, and liquids behave. But the main difference between, if we look at something in the gaseous phase and the liquid phase and the solid phase, is the magnitude of the intermolecular forces that are acting between them. Okay? If we look, okay, so, what's the difference? So in a gas, okay, if we look here first at a gas, molecules that are in a gas are spread far apart and they have a comparatively high kinetic energy, meaning that they're going to be moving around. So if we look at these gas molecules here and on my flask, they're moving around here really fast. okay? And they're not really held to each other that much. The reason why that is because their kinetic energy and their speed is such that when they meet another molecule of the same type, like say, for example, that this one right here meets up with that molecule right there, these will be attracted to each other by one of three intermolecular forces of attraction we're going to talk about here today. They will be attracted to each other, but the attraction is relatively weak. It's easy for them to break free of each other and to go their separate ways. If we look at the molecules here in the liquid state, okay, here in my beaker, the difference between this and the gas phase is that these molecules are packed more closely together, and so the attraction that they feel for each other is greater. Another way you can think about it is that if these molecules were all put into a room together, the degree of attraction that they would feel for each other at that particular temperature is great enough that to hold them into a liquid state. So they're attracted together more than they want to fly apart, basically. And if you look here in the solid, okay, so for the solid phase, or anything in a solid phase, the intermolecular forces of attraction are even more prominent, they're even stronger. So that's really the difference here between these three phases. If we compare the three, solids, liquids, and gases, if we compare substances that are at the same temperature, for a solid, the degree or the magnitude of intermolecular forces will be greatest, okay? The liquids is going to be somewhere here in the middle, and the gas is going to be the least, okay? And the rationale for that would be that in the gas phase, the forces are so weak, the forces acting between molecules are so weak that they cannot be held very close together. They have too much kinetic energy. Whereas here in the liquid, they're held together more, and here in the solid, they're held together in the most rigid arrangement possible. Okay, so that's how that relates to solids, liquids, and gases. Okay, so there we go. Okay, now as a result of the way the molecules are packed into solids, liquids, and gases, because we're going to talk about the structure of solids and liquids here a little bit, the differences are these. Gases, okay, can be compressed, meaning that because there's a whole lot of space between the molecules in a gas, if you apply a force, you can squash them close together and eliminate some of that empty space. Whereas liquids and solids have low compressibility. The reason why that is because in a liquid and a solid, okay, the molecules are already pretty close together. There's not a whole lot of empty space, and so you cannot easily squish them closer together, okay? And generally speaking, like we just said, solids and liquids have stronger intermolecular forces. If I look at substances at 25 degrees Celsius and I compare them, and I compare things that exist as solids and liquids to things that exist as gases, these solids and the liquids have the greater, stronger, I should say, intermolecular forces holding the molecules, or attracting the molecules to each other, okay, and to turn those into a gas would require some energy. So there we go. All right, so let us talk now about the types of intermolecular forces. Okay. When we talk about intermolecular forces, these are the forces that attract, or that hold solids and liquids together, and that also attract all molecules of different types to each other. We're going to talk about this force of attraction. You should know that these forces of attraction are much weaker than ionic or covalent bonds. A chemical bond is way, 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 way stronger than any type of intermolecular attraction that we're going to talk about today. Let's consider an example. This is HCl right here, and this is showing here a diagram here where we have one molecule of HCl here and one molecule of HCl here. These molecules are attracted to each other in a way that we're going to talk about here in a moment. Okay, these separate molecules here are attracted to each other, but the molecules themselves are also held together by an attractive force, by these covalent bonds. Now, if we heated the sample up of HCl, okay, and we're trying to break the attractions here between molecules, it takes only 16 kilojoules per mole to vaporize hydrochloric acid, or to vaporize hydrogen chloride, meaning if we had pure hydrogen chloride in a vessel and we applied energy to it, it would require 16 kilojoules per mole to vaporize, to change it into a gas, or in other words, to break this attraction between the molecules. Because really, when something goes from a liquid to a gas, what you have to do is you have to break the intermolecular forces of attraction working between the molecules. So to do that for HCl would take 16 kilojoules per mole. Compare that to the amount of energy it would take to break the chemical bonds. it takes 431 kilojoules per mole to break the covalent bonds within the HCl molecules. So that takes way more energy, guys, to break these covalent than it takes to break the intermolecular forces of attraction. So just keep track, guys. Always, 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 intermolecular forces of attraction are always weaker than covalent bonds. Okay? So there we have it. And just keep in mind that when we have a state change, really what we're changing is all the time we are changing the intermolecular forces acting between molecules. If something goes from a solid to a liquid or a liquid to a gas, okay, intermolecular forces are being broken. And if we go the other direction, either something condensing from a gas to a liquid or a liquid into a solid, new intermolecular attractions are forming. All right. Now, the types of intermolecular forces that we're going to talk about today fall into 3 or 4 different categories. You have ion-dipole attraction, dipole-dipole attraction, and hydrogen bonding and London dispersion forces. Okay. Now, these collectively, these 3 right here are often referred to as van der Waals attraction. Okay. These are, now you may have heard just dispersion forces, London dispersion forces being referred to in the past as van der Waals attraction. Really, these 3 right here can all collectively be referred to as van der Waals attraction, but they really are different things, actually. Okay, so these are the 4 types we're going to be talking about today. We're going to go through them one at a time. But keep in mind, as we are going through, that intermolecular forces of attraction really are what determine the properties of molecules. So when you, or properties of substances. So when you look at something, for example, that has we look at the boiling point or the melting point of a substance, that temperature at which something melts or boils reflects how strong the intermolecular forces of attraction within that substance are. The higher the the higher the boiling point, okay, something boils at, the stronger the intermolecular force of attraction will be for that substance, because a high boiling point means that it takes lots of energy, okay, I'll just write that down here, guys, lots of energy to break or to overcome the intermolecular force of attraction within that substance, okay. Same thing with a high melting point. The reverse is also true. If something has a very low boiling point and it changes to a gas easily, what that means is that the intermolecular force of attraction within the molecule within the substance are pretty weak. Okay, so the properties of a substance are a reflection and are determined by the intermolecular forces of attraction. Keep that in mind. All right, our first intermolecular force is going to be ion-dipole attraction. Now, what this is, as the name would suggest, is it's the interaction and the attraction between an ion and a dipole. And if we were going to rank the types of intermolecular attractive forces according to strength, this would be the strongest one. Okay. Now, as an example, okay, let's look at it here, guys. An example of what this is right here would be if we consider here the potassium cation, K+. This is a positive ion. This is attracted to a water molecule. Here is H2O right here. Now, as we saw in the last unit, because of the shape of the water molecule, okay, and due to the fact that these bonds are very polar, so hydrogen here has a partial positive charge, oxygen has a partial negative charge, each of these bonds, the oxygen-hydrogen bonds, is polar, and if we look at the water molecule, it has a net dipole moment where the vector would be pointing that way towards the oxygen because it is the negative end of the molecule. Well, since this is negative right here, this is going to be attracted to this positive ion right here. That attraction, guys, is an ion-dipole attraction, okay? And so for water, you can imagine that all positive ions are going to be attracted to the oxygen in a water molecule, and this is the primary reason why things like sodium chloride, for example, are soluble in water. When sodium chloride dissolves, you get a sodium cation, and you get a sodium cation and a chloride anion. That sodium ion is attracted to the negative oxygen in the water molecule. And so you can kind of think that what's happening when a salt dissolves is that the water molecules, which are attracted to the positive ions, are sort of pulling those off of the crystal of sodium chloride. In a similar fashion, guys, this end of the molecule down here is positive. So if I asked you, well, what kind of ions would be attracted to the positive end of the water molecule, you'd say, well, Mr. Harper, of course, negative ions would be attracted to this side. So if, for the sake of argument, a chloride ion was to be found down there, this end of the water molecule will be attracted towards that, because this is negative and this is positive right here, and they will attract. Okay. So that is what an ion-dipole attraction is. It's the attraction between a polar molecule, or the one side of a polar molecule, and an ion. Now, the strength of this attraction is determined by three factors. And number one, the distance between the ion and the dipole, or the distance between the ion and the positive or negative end of the molecule. Obviously, the shorter the distance, the stronger. Okay, the shorter the distance, the stronger the attraction is going to be. If we consider these examples down here, if we look at potassium and lithium and magnesium, actually let's just look at, no, never mind, not that one. Let's just look at potassium and lithium right here. Lithium is a smaller cation than the water than potassium is, and what that means is that because it is the smaller cation, it can more closely approach the water molecule. So here we have the distance, okay, between the ion and the water molecule. Here is 78 picometers. Here it's 133 picometers. You can see that for lithium, the attraction, okay, the ion-dipole attraction, the magnitude of the attractive force between these two things is much higher than it is over here for the potassium and the water molecule. So the shorter the distance between the ion and the dipole, the stronger the attraction is going to be. The second thing that affects it is the charge in the ion. Obviously, the higher the charge on the ion, okay, the stronger the attraction is going to be. If again we consider the lithium plus cation and we compare that to the interaction between magnesium 2 plus and the water molecule, these have pretty much the same distance between the ion and the water molecule. Here you can see this is 79 picometers between the ion and the water molecule compared to 78 picometers here for the lithium ion. But the attraction for magnesium between magnesium and the water molecule is way higher, negative 1922 kilojoules per mole compared to negative 515. This is because magnesium is a 2 plus ion. It has a higher charge, and hence we have to have a stronger attraction between itself and the water molecule. Lastly, guys, the magnitude of the dipole, the more polar, okay, a molecule is, the stronger this attraction is going to be, because a strong or a large dipole corresponds to a very polar molecule with a more positive, more negative end on it. So there we have it. That's our first type of attractive force, an ion-dipole interaction. Okay, now obviously you're going to see this for ions and things that are polar. This is extremely important for soluble salts, because this is the entire reason that your things like sodium chloride and potassium nitrate and all these soluble ionic compounds, this is the entire reason that they dissolve in water, is because there's a very strong attraction between the ions and the very polar water molecule. All right, our next type of intermorphic attraction is the dipole-dipole attraction. Now, as the name suggests, this is going to be the attraction between two dipoles, or in other words, this is going to be a type of attractive force that is going to exist between polar molecules. All polar molecules will experience this type of interaction. Now, keep in mind, guys, a polar molecule is one that has a positive end like this and a negative end like this. You can imagine that if two polar molecules approach each other and are near each other in space, the positive end of this one molecule will be attracted to the negative end of this other molecule here, and that attraction between the positive side of one molecule and the negative side of another molecule is the dipole-dipole type attraction. Generally speaking, this type of attractive force is weaker than an ion-dipole attraction, okay, but it's still comparatively strong if we compare it to other intermolecular forces, okay? And how strong it is, of course, is not the same strength for same force of attraction for every type of molecule, for every molecule. Generally speaking, the strength of the attraction increases as the polarity increases. So, in other words, polarity, guys, remember, this is measured by dipole moment. So, the higher the dipole moment on a molecule, the greater the strength, the dipole-dipole attraction that those molecules will have for each other. So let's take a look here, guys, at this table down here. This is out of a different book than yours. It's out of the Brown and LeMay textbook, but I appropriated it. what we have here is a series of molecules. So we have propane, dimethyl ether, methyl chloride, acetaldehyde, and acetonitrile. And these all have molecular weights that are in about the same range. And if we consider these molecules here, we have the dipole moment in this column. So the dipole moment measures the polarity. Again, the higher the number, the more polar the molecule is. So if we look here at propane, it has a dipole moment of 0.1. This is a very non-polar molecule, has a very weak dipole moment. If we look down here now, as we go down this list, the dipole increases until we get down to acetonitrile, which is a fairly polar molecule with a dipole moment of 3.9. If we compare the boiling points of these different substances, propane boils at 231 Kelvin, so actually below room temperature, and we go up to dimethyl ethers, 248, then 209, and then we go up to acetaldehyde, which is more appreciably polar. That boils at 294 Kelvin, and then finally acetonitrile, which is 355 Kelvin. You can see, guys, as we go down this list, as the molecules become more polar, the boiling point increases. Now, remember I said before that boiling point is kind of a proxy for the strength of intermolecular forces. The boiling point depends on how strong the attraction between molecules is. The higher the boiling point, the more strongly they are going to be attracted to each other. Okay? So you can see that as we go down this list, it makes sense the boiling point would go up because the dipole moment, as you go down the list, goes up, and it becomes more polar, and hence the attraction becomes stronger. So there we go. That's the physical impact of this dipole-dipole type attraction. Now, on the slide here, I had this picture of single molecules showing this sort of dipole-dipole attraction for each other. But just the picture I want you guys to keep in your mind is more like the one that's on this slide. If you picture in your mind the bulk substance, what I mean by bulk substance is you have a lot of something. So, for example, if we're looking at our glass of water, we have jillions and jillions of water molecules. If we're looking at a flask full of propane or a flask full of dimethyl ether or something, we have a bunch of dimethyl ether molecules. Okay, you've got a lot of molecules that are near each other. So in the bulk substance, what you're going to see is something sort of like this. You've got a whole bunch of molecules with a positive and negative end if they're polar. Okay. Now these molecules, because they're in close contact with a bunch of other molecules with a positive and negative end, there are many separate attractions between molecules. And it is the sum of these intermolecular attractions between a bunch of molecules in the condensed phase that is what determines the boiling point or the melting point of the substance. So that was just kind of the point of the slide. I want you guys to keep that in mind, that in the bulk substance, we've got tons of molecules, not just one or two. Okay, and those molecules, when they're packed close together, many of them will feel attractions for each other, not just, one. Okay. A subset, a special case of dipole-dipole attraction, which is very important, is hydrogen bonding. And the reason why this is so important is because this is way, 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 way stronger than the regular dipole-dipole attraction. Okay. Now, of course, one thing you remember from biology and from normal chemistry is that this is extremely important for water. Okay. Hydrogen bonding is very important for water, and it's the entire reason why water has got such a high boiling point and a high melting point relative to other molecules of comparable molecular weight. Okay. Now, what this requires, in order for something to be capable of forming hydrogen bonds. Now, keep in mind, guys, this is not a real bond. When we say, chemical bond, we think covalent bond, we think ionic bond. What we're talking about here is an intermolecular force of attraction, so make sure you keep that clear in your brain, not a shared pair of electrons. Okay? But what this requires is that the hydrogen atom in something has to be bonded to a small, highly electronegative element. Now, this is really only going to be cases where hydrogen is bonded to either fluorine, oxygen, or nitrogen. Okay? So here's the reason why that is. If we look at the water molecule once again, okay, here we go, dot, 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 and we compare the electronegativities of the bonded atoms here. Oxygen has an electronegativity of about 3.5. Hydrogen here is about 2.1. So the difference in electronegativity delta chi is like 1.4. This is a very polar bond. Okay. Now, what that means is that when the water, if we look at the water molecule, the hydrogen here has a partial positive charge, the oxygen here has a partial negative charge, but those are fairly substantial partial charges because the bond is so very, very polar. Okay, so that's why. Now, when this is really polar, okay, what that means, we talked, before about dipole-dipole attraction. Really, what this is right here, hydrogen bonding is a special case of dipole-dipole attraction. When we have something which is very polar, as in the case of water, we know that the attractive force between those polar molecules is going to increase. Okay, for the water molecule, or for cases where we have hydrogen attached to fluorine, oxygen, or nitrogen, and other molecules, that leads to a very polar bond and a very polar molecule overall, which means that the magnitude of the attraction between that molecule and others of the same type is going to be very, very, very strong. That is hydrogen bonding. It's just a special case of dipole-dipole attraction where we have a really, really polar molecule. Okay, and the other requirement is that you have an unshared electron pair on a different atom somewhere nearby. So usually this is going to be something that has a lone pair of electrons like fluorine, oxygen, or nitrogen. Okay, so here's how this works. We're going to consider, again, here just water as our example. So if we look here, here's an isolated water molecule. We said before that the hydrogen here has a partial positive charge. The oxygen here is going to have the negative charge. We have negative, positive, positive. Now, when a bunch of water molecules get near to each other, each of these water molecules has got a lone pair of electrons, okay, up here, or two lone pairs of electrons, I should say, really here, distributed someplace about the oxygen atom, okay? And the hydrogens here all have that partial positive charge. Partial positive, partial positive, partial positive, partial positive. You get the idea. Okay, so these are all positively charged. So these are going to be attracted to each other. These molecules will be. Here's the negative end of the molecule. This is attracted to the positive end of this molecule right here. But it's also attracted to the positive end of this molecule right here. And this hydrogen here is attracted to the negative end of the molecule there, and this is attracted to that negative end of the molecule there. And this hydrogen down here is attracted to the negative end of this water molecule, and this hydrogen is attached to the negative end of that water molecule, and this hydrogen is attached to the negative end of this water molecule, and so on and so forth. So you have these attractions between the positive and negative ends of the water molecules. And there you go. And that attraction is very, very strong because these bonds are so very polar. Now, in order for this to happen, again, it has to be that the oxygen atom here has got these lone pairs of electrons because that's an integral part. Because this hydrogen here is so positive, it wants to be near electrons. It wants electron density. It desires electron density because its electrons are being stolen away from it. So that's part of that attraction, is that it is trying to get at these lone pair electrons here on the oxygen, okay, in the water molecule. Okay. Now, if we look at the effect this has on the properties of the substances, okay, what we're looking at here on this chart, and there should be a similar one in your book, is the boiling points, okay, of different hydrides. So this line right here is the group 6 hydride. So we have here water, H2O, hydrogen sulfide, hydrogen selenide, and hydrogen telluride. So this would be the group 7 hydrides. So we have hydrogen fluoride, hydrogen chloride, etc. Here's to be the group 5 and the group 4, just for the sake of argument. Now, if we look at the boiling point of water compared to the rest of its groups, so the next compound formed between a group 6 element and water would be hydrogen sulfide down there. We can see that the boiling point of the water molecule is way, 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 way higher than the boiling point of hydrogen sulfide. The reason for that is because of this extremely strong hydrogen bonding attraction between the water molecules. Hydrogen sulfide is not capable of doing the same thing, and here's why. If we look at the Lewis structure of the hydrogen sulfide molecule, okay, it looks something like this. The hydrogen down here, again, is going to have a partial positive charge, and the sulfur is going to have a partial negative charge, but the polarity of this bond is way weaker than it is for the water molecule because the difference in electronegativity is not as high. Because the molecule is not as polar, the attraction between hydrogen sulfide molecules is less than between water molecules. A second reason for that is because if we look at the size of the sulfur, okay, in hydrogen sulfide, sulfur is way larger than oxygen is, and so when hydrogen sulfide molecules are trying to get near to each other, they can't get as close due to the size of the central sulfur atom. For instance, they're getting quite as close to each other as the water molecules can. So those two reasons are why the attractive forces in hydrogen sulfide are not as strong, and hence the boiling point is lower. And we see the same trend for hydrogen fluoride and for ammonia also. Okay, these molecules have much larger boiling points than other hydrides in their group. So if we can flare hydrogen fluoride to hydrogen chloride, the boiling point here is way lower, or way higher rather. If we compare the boiling point of ammonia to that of phosphine right there, pH 3, it is also way higher. Okay, now if we look down here at methane, okay, we can see that in the case of methane and the other group 4 hydrides, you see a very different trend. You see that the boiling points kind of linearly increase as you go down the group and as you go to larger and larger molecules. The reason for this is that these molecules are all non-polar, okay, and they are not capable of dipole-dipole attractions or of hydrogen bonding. They have a different type of intermolecular force of attraction, but in the absence of hydrogen bonding, this right here is the trend you would expect to see. And the entire reason for this bizarre trend over here is the abnormally strong intermolecular attraction between ammonia molecules, water molecules, and hydrogen fluoride molecules, which would look something like this. So if we have our fluorines bonded to our hydrogens, okay, that's kind of a terrible drawing, but you guys get the idea. Okay. Now, how do you know what can have hydrogen bonding and what can't? Because you're going to say, well, Mr. Harper, this is kind of complicated to remember. Here is your guideline. To determine if something is going to participate in hydrogen bonding, if it is capable of participating in hydrogen bonding, you're going to follow a very simple rule. What I usually ask people is, what does E.T., who is this guy, for those of you guys who have never seen E.T., that is E.T. right there. What he says throughout the movie, he's an extraterrestrial in case you guys didn't guess, he wants to phone home. He says all the time, E.T. phone home. That is his trademark line. Well, guys, it's an easy thing to remember. What can hydrogen bond? It can hydrogen bond if it can phone home. If you have hydrogen, which is bonded to either a nitrogen or to an oxygen or to a fluorine, okay, if you have a molecule where the hydrogen is attached to one of those 3 elements, either fluorine, oxygen, or nitrogen, then that substance will be capable of hydrogen bonding. There we go. All right. Our next type, oh goodness, my movie will not work evidently. So guys, this was supposed to be a movie right here, a little clip, but I guess that's not going to work with this podcast program, so that's okay. We'll improvise. The next type, and the last type, actually, of intermolecular force attraction we're going to talk about today is something called London dispersion forces. One thing you want to keep track of is that these are the weakest type of intermolecular force of attraction. They're the weakest, but they are still very important, okay? Now, what this is between, we saw that ion-dipole interactions were between the charged ion and the positive-negative end of a molecule. Dipole-dipole attraction was between the positive and negative ends of molecules that have positive and negative ends. Hydrogen bonding is a special case thereof. London dispersion forces is the same basic idea. It is the attraction between the positive and negative ends of molecules. But this is between something called instantaneous dipoles. Okay? This is a type of attractive force that you see for all molecules, but which is most important for things that are non-polar and are incapable of being attracted to each other through either hydrogen bonds or dipole-dipole attraction or ion-dipole interactions. Okay? Let's consider, for example, to illustrate what this is, the element helium. Okay? Helium, guys, is a noble gas. If we look at helium, each helium atom has 2 electrons. Okay? So these diagrams down here both represent helium atoms. Okay? Now, if you can imagine, if you look at these helium atoms over all time, okay, if you were to somehow be able to track their electrons and kind of watch where they go, you would expect that over time, the electrons in the helium atoms are going to be roughly spherically distributed. They're going to be evenly distributed overall. And so overall, a helium atom, obviously, guys, is nonpolar. But if you look at a helium atom at any given instant in time, okay, so we consider these two electrons right here. These electrons move independently of each other, and they move randomly. Well, roughly randomly. I mean, we think, sort of, kind of. But keep in mind, we can't tell where an electron is at any given point in time. That's the uncertainty principle. But we assume they move fairly randomly. Now, it could happen that both of these electrons could move over in this direction at a particular instant in time. Now, if that happens, you're going to have something like this, where the electron cloud is distorted. There's more electron density over on this side over here, and there's less electron density over here. When that happens, what that means is that for just an instant, this side of the molecule will get a partial negative charge, and this side over here is going to get a partial positive charge. Now, if this happens on another helium atom here, where its electron cloud gets distorted, so it has a partial negative side and a partial positive side over here, then for a moment you're going to have the attraction here between the positive and negative ends of these molecules. Now, because this dipole that forms here, okay, we could draw an arrow here showing this is a polar molecule, or not a polar molecule, a polar atom, and so is this for an instant. Because this is an instantaneous induced dipole, it does not last, it's going to go away, and it's only lasts for just a second, okay? This is called an instantaneous dipole attraction. It's very weak, okay? But if you imagine if we have a sample of helium, you know, and we have all these helium atoms here that are in that sample, this sort of thing can be happening with any of them in any given instant in time, and in the next instant, it goes away. It goes back to be like this. But then maybe the electron cloud gets distorted in the other direction an instant later, and so then you have the negative side over here and the positive side over here, and now again, those atoms are going to be attracted to each other. That, you know, very, very, very blindingly, you know, faster than you can blink fast. This is happening all the time if you look at a sample of a substance. At any given instant in time, the electron cloud can be distorted in some direction. That gives rise to an instantaneous dipole in the molecule. For just a second, it has a positive negative charge, and that instantaneous attraction between the positive side of one thing and the negative side of another thing leads to attraction between atoms and between molecules. Now, this type of attraction is present for all molecules, because things, whether they're polar or non-polar, okay, this can happen with any of them. So this force is the weakest of all intermolecular forces, okay? But it exists between all molecules and all atoms because any of them can get their electron cloud distorted, or it can happen to them at any given instant in time, okay? And we already said why this is called London dispersion force is because of the attraction between instantaneous dipoles. Now, we said that you know, dipole-dipole attractions increase as things become more polar. Well, the magnitude of dispersion forces increases when they become more likely and more capable of having these instantaneous dipoles. In other words, the more electrons something has, the easier it can form an instantaneous dipole, and the stronger, and you know, the more readily they'll be attracted to each other, and the stronger those attractions are going to be. Okay, we call this capacity, okay, to form these instantaneous dipoles, polarizability. Okay, the more polarizable something is, and the more electrons it has, okay, the easier it is to create these instantaneous dipoles, and the stronger and the more important this attraction is going to be. Generally speaking, if we're comparing molecules of similar structure, the degree and the magnitude of London dispersion forces will increase in strength as the molecular weight increases. Or in other words, as the molecules get larger, this attraction is going to become stronger. Okay? So to illustrate this point, let's consider the halogens. These exist, as we know, as diatomic molecules F2, Cl2, Br2, and I2. If we just look at the Lewis structure of one, which is fluorine right here, you can tell that the fluorine molecule is overall going to be nonpolar because the bond is nonpolar and the shape is symmetrical. Okay, but separate fluorine molecules, okay, can be attracted to each other through this sort of instantaneous dipole attraction, so between these dispersion forces. So these two fluorine molecules will experience a weak attraction for each other due to this type of attractive force. So because for fluorine, this force is relatively weak, it has a very, very, very low boiling point, 85.1 Kelvin, which is at a temperature far below the freezing point of water. So that's why fluorine at room temperature is a gas, because it boils way before room temperature. As we go down the group, okay, as we go from fluorine down to iodine, you can see that their molecular weight goes up, and also their boiling point is going up. Their boiling point going up would should cause you to realize that the degree of attraction between molecules of these halogens increases as you go down the group. The reason for that is because as the molecules get bigger, okay, as we go from fluorine down to iodine, they're getting more and more electrons, the molecules become more polarizable, and so the attractive force between those discrete molecules is going to increase. You can see the same trend here, guys, if you take a look here really quick in this table of the noble gases. As you go down this group, as you go from helium to xenon to heavier and heavier molecules with more and more electrons, as their molecular weight goes up, you can see that their boiling point is going to increase, okay, because of the fact that the force of attraction between the particles gets stronger because they get more electrons, become more polarizable, okay? So that's one factor that affects the strength of dispersion forces. A second one actually is a little bit tougher to understand. It's surface area. So the more electrons something has, the larger the molecule, the more polarizable, the stronger the magnitude of the dispersion forces acting between them is going to be. Well, it turns out that the dispersion force magnitude does not only depend on the size of the molecule and the number of electrons, but also on the surface area. The greater the surface area that's available for contact between the molecules, the greater the force of attraction. And that makes sense because there's more interaction possible between the molecules. So to illustrate this point, we're going to look at an example. This is a space-filling model of the molecule N-pentane, and this is neopentane. They both have the same molecular formula, which is C5H12, but these molecules are examples of something called isomers. They have the same formula, but different structures, different arrangements of the atoms. You can see that this one right here has got the greater surface area. There's more possible attraction and interaction between these molecules in the space there than there is between these neopentane, or between the two neopentane molecules over here on the right. Because there's less surface area for these molecules, there's less attractive force between them, and so if we compare the boiling points, the boiling point here of neopentane is lower than that of pentane right there. So there we have, guys. It's London dispersion forces. Now, I told you guys before, these are the weakest intermolecular forces of attraction, but they're very important because these are what's at work between all different kinds of molecules, but they're the only type of attractive force that is possible for things that are nonpolar. One particular application, or one way that you can, or one place you see dispersion forces in nature is one of my favorite creatures are geckos. As you guys know, geckos can stick to walls. They can run up glass and stick to surfaces that most people, you would otherwise think are slick. And this is an example of a gecko right here. This is my good friend Brick. He is a red crested gecko, which is crested geckos. Their scientific name is Rhacodactylus ciliatus. They're really cool. They were thought to be extinct until 1994. Very, very cool lizards. Now, I have seen him run up all kinds of different slick glass surfaces. He's run up my walls several times. The reason he's able to do that is if you look on the bottom of a gecko's feet, they look like they're covered in bunches of little itty-bitty tiny hairs. What allows them to run up a glass surface is that when each of those hairs gets near to the glass surface, there is a dispersion force attraction between the molecules on the surface of that hair and the surface of the glass. And because there's billions and billions and billions of those attractions that are possible between each of his toe pads and the glass, even though each attraction is not very strong, the sum of the forces is strong enough to give him traction and to enable him to run up the glass. So the reason I point this out to you guys is so that you keep in mind that even though the attraction between two nonpolar molecules may be weak, when you take the sum of the attractive forces that are in a sample of some nonpolar substance, when you have billions of those attractions going on at once, they're all together, with their powers combined, can be relatively strong. Okay, guys, so we are nearing the end of our podcast here. Just to sum up really quickly, I want to look here at the strengths of the different types of intermolecular forces of attraction, and I want to contrast these with the strengths of different types of bonds. If we look at ionic bonding, covalent bonding, and metallic bonding, the three kinds of bonding we've talked about, okay, if we look at the energy that it would take to break the bond between a cation and an anion, it's somewhere in the area of 400 to 4,000 kilojoules per mole, so that's a lot of energy. If we look at a covalent bond, those tend to run between 150 and 1,100 kilojoules per mole to break those bonds. And to break metallic bonding, it requires usually somewhere between 75 and 1,000 kilojoules per mole. So that's a lot of energy to break a real bond. If we contrast this with the amount of energy it takes to break intermolecular forces of attraction between molecules, okay, ion dipole attractions usually are somewhere in the area of 40 to 600 kilojoules per mole. Now you should notice that's pretty strong, guys. A lot of times ions can be very strongly attracted to water molecules, which is why you have those hydrate things we've learned about, like, for example, copper sulfate pentahydrate. Why you get these hydrate compounds is because of this very strong attraction between the cations and the water molecules, okay? So you can see sometimes this runs into the range of a real chemical bond, but not real often. Hydrogen bonds, in contrast, have a dissociation energy usually between 10 and 40 kilojoules per mole. So you can see that this is what we were talking about as being the second strongest kind of intermolecular force of attraction. This is like 10 times less energetic than a covalent bond. So it takes way less energy to break intermolecular forces of attraction than it does to break a chemical bond. In a similar way, if we go down the list, dipole-dipole attractions take usually between 5 and 25 kilojoules per mole, and London dispersion forces usually between 0.05 and 40 kilojoules per mole to break that sort of attraction. So you can see that these, the main point I wanted to make with looking at this was that the intermolecular forces, guys, keep this in mind, these are always weaker than bonds. Okay? And one example, and then I'm going to cut you guys loose for the day. Okay, an example. I want you guys to look at these molecules and identify, okay, pause the podcast here for a moment, and identify the intermolecular forces that act between molecules of each of the following compounds. Okay, pause it for a second. Okay, we're back. To check your answers, guys, if you look at HCl, this can experience dispersion type attraction, okay, dispersion forces, or you could call these London dispersion if you wanted to, but the reason these are called London dispersion forces is because a guy named London, his last name was London, did a lot of research with them. So you don't have to say London dispersion, you just say dispersion attraction if you're listening to them. And also, besides dispersion forces, you're going to have dipole attraction, because if you look at the HCl molecule, it is in fact a polar molecule, and it has a net dipole moment. So going that way, since it's a polar molecule, it is going to experience dipole-dipole type attraction. Notice, though, I did not include on the list hydrogen bonding because it does not meet our phone home requirement. Hydrogen is not attached to a nitrogen, oxygen, or fluorine. Nextly, hydrogen fluoride. This can experience dispersion forces and also hydrogen bonding. Now, because it can experience hydrogen bonding, since this is sort of a subset of a dipole-dipole type attraction, I would not list dipole-dipole attraction and hydrogen bonding. I would just say hydrogen bonding, because I understand that this is a polar molecule. Okay, now it's hydrogen bonding again because this meets the phone home requirement. The hydrogen is attached to the fluorine, and this bond is extremely very polar, where this has a very big negative charge and this has a big positive charge. And methane, if we look at methane right here, the type of intermolecular force of attraction that this can experience would just be dispersion forces, because it is totally nonpolar, cannot experience a dipole-dipole attraction or hydrogen bonding. It can only experience dispersion forces because it is a nonpolar molecule. And if I was going to rank these molecules in terms of strongest intermolecular forces of attraction to weakest, it would go in this order. Hydrogen fluoride has stronger intermolecular forces of attraction than HCl, which should be stronger than methane. And what you would expect to observe for these molecules, if you're going to observe the boiling points, is that the boiling point of hydrogen fluoride would be greatest, followed by the boiling point of hydrogen chloride, followed by that of methane. That's the impact of intermolecular forces of attraction. Okay, guys, the part you have all been waiting for, assignments. What you're going to do with this now is go and apply it to some problems. Assignment 13, or chapter 13, assignment 1 is going to be these problems right here. It is going to be problems number 16 through 31. Okay, there we go, out of your book. Now, these are not going to take you very long because there's not any calculations involved in this stuff. It is all just qualitative and looking at things and you know, being able to predict intermolecular forces and properties and that sort of thing. But I would also strongly exhort you to read the section of the book pertaining to intermolecular forces of attraction so that you can go through and read it in different terms and have that much greater knowledge about that. Okay, guys, thank you very much for watching the podcast. Now, go forth and do chemistry. I will talk to you next time. See you later. Bye.